Okay, I think we're on time. Hi everyone, my name is Gil Tene and we're going to be talking about priming Java for speed. This will be a talk about the kind of optimizations you find in a JVM, and not just looking at the optimizations themselves, which we'll spend a bunch of time on, but also at the dynamic nature of optimizations. We have some things in managed runtimes that let us do dynamic and speculative optimizations, which are very powerful, but they also mean that the speculations are sometimes wrong, and we then have the reverse effect of dynamic optimization, which is deoptimization, which is one of the issues that we run into a lot and we've spent some time working on. As a high-level agenda, what I'm going to cover is, I'll start with an introduction, just some background on the subject. Look at the realities of how Java behaves in systems that are response-sensitive or speed-sensitive during periods of a time, and what kind of problems we're facing there. And then we're going to spend a lot of time talking about compiler optimizations. You don't have to have a compiler optimization background to understand this. I'll start simple and build up from there. And if you actually look at the rest of the talk, probably most of the subject here will actually be how compiler optimizations work in a JVM. We'll then talk about the optimization, talk about the problem itself, and look at some demonstrations of that happening, and then talk about what we can do about it. A little bit of background about me. I'm Gil Tene, I'm the CTO of Azul Systems. At Azul, I work on all kinds of things. Probably the best known thing I've been working on is garbage collection. We basically believe we've solved garbage collection. It's done. You don't have to worry about it anymore if you use the solution we have. No tuning, no thinking. A year after you do this, you forget about the bad nightmares of reading GC logs and all that. Here's some evidence of me actually working on garbage collection. This picture was taken in my kitchen. That machine is a trash compactor. And the job of a trash compactor is to compact the garbage in place multiple times during the week so that you delay the full GC to the weekend. That way you take the bag and you take a big pause and you put it in the outside thing. Right? It's a very useful machine, but in this case it stopped working. There was a bug in it. Fragments were not being defragmented right. I had to open it up and work on it. So I thought it would be funny at the time to take the GC book and take a picture. The most important piece of information here is that this picture is from 2004. So I've been thinking this is weird and funny for a while, and I really do need a new picture. But this talk is not about GC, and this is just some nice background. At Azul, we make JVMs. We make JVMs that improve latency, improve speed, improve consistency, so we measure these things a lot. Zing is our flagship JVM. Zulu is our binary build of OpenJDK. But we spend time on this problem. And really, once we've solved garbage collection, the number one complaint, the number one request we've gotten in the history of the company was for us to work on this problem that I'll talk about today, which some people call the warmup problem, some people call the slowdown problem, the deoptimization problem, there are many names for it. But people have come to us and asked us to do it. And when the first few people asked us to do it, I was kind of, really? I mean, does this matter? Actually, one of them is right here. But I actually keep a counter of how many times people ask me to do things without me asking them what they want me to do, and for different features. And it's a good way to figure out what we actually want to work on. And this reached 23 by now. Well, now we do it. And the biggest other number I've had in the history of me doing this is 6. So this is the most requested feature by far. By the way, nobody asked us to solve garbage collection. We just did that. Okay, so let's look at some motivation. What kind of problems are we talking about? Now, this is not unique to trading. You could find this problem in in software rollout of new versions and starting up clusters or shrinking them down. There are many useful applications for this, but a market open condition is a great demonstration for the problem. When you have a market, when you're about to trade, and the market hasn't opened yet, it's about to open, there's this interesting situation where everybody is waiting for the gun to go off to start the race. The beginning of the market is the most volatile, most risky, and most profitable part of the market to trade in, the first few seconds or the first, until things settle down into the normal day behavior. And we actually have customers that make half of their entire profit in those first few seconds of the day. So how fast you are right then, not on average, not later, but right then, is important. Which means obviously you're going to get ready for it and get ready to be fast. So, ready, set, go, right? Well, unfortunately with Java, this is what usually happens. The ready set is up there, but then right as the market open, you go slow. And then later you go fast again. So if you actually measured averages, you wouldn't even know this happened. But those first few seconds, first minutes sometimes, but first few seconds are very slow. And what's going on here? Why does this happen? This isn't actually warm-up. It's a slowdown after you were fast. And what actually happens is this. In Java, we start slow. We start interpreted usually. And then we learn pretty quickly. So as code starts running, we notice what code is running, what is hot, what is cold, and we start paying attention to the hot-cold. And if you look at the latest versions of most JVMs, that's even done in tiers. First you compile it one way, then the things that are even hotter than that you compile in another way. But you basically learn and you optimize, and you load classes that aren't even loaded, and you initialize things, and then you aggressively optimize what is hot. You actually pay a lot of attention to the code that is really running, to how it is running, and you optimize to get that code to be fast. Some of those optimizations are speculative. Some of those are based on the fact that the code has been behaving a certain way, so let's make it fast for that way of behaving. But then, sometimes those speculations are wrong. And when they're wrong, we temporarily have to throw away that optimization, run slow for a while we learn again how to run fast. And then we go fast again and we stay fast. That's the typical curve of behavior for a Java virtual machine as it starts. Right? Slow, faster, 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 a little bit of slowness, and then fast again. This is especially true for very short operations that need to be very quick. So this first part is what you would normally think of as warm-up. You started slow, you went fast. This last part is deoptimization. And I'll get into that in detail later. So with this introduction, and remember this could be a trading day or it could be the startup of your 100 server cluster because you just rolled out a new version of code, that dip happens. Okay? And the warm-up happens. So with this, let's look at some compiler stuff. And as I said, I'll start at the basics and go up from there. So simple compiler things. Let's look at some optimizations and how compilers transform the code or what they're allowed to do. So here's a simple reordering of instructions example. We have a simple set of instructions up there. And the compiler is allowed to rewrite the code to effectively do what the bottom code is doing. The reason it's okay to do that is because the effect of that code is identical. Right? The point at which that operation, C equals Z plus X, happens doesn't affect any output, doesn't affect the meaning of the program. So the compiler is allowed to change the order of things in the code. There's nothing in your order that says you can't do that unless you explicitly use things that make reordering not happen. So this is a common side effect or optimization. Now, another common optimization is we can eliminate code that is dead, code that doesn't actually have a side effect. If we can prove that we don't need to run it because nobody will know if we didn't run it, then we're allowed to take it out. That instruction has no effect on output. No matter what order it runs on, we don't even need to execute it. So when the compiler compiles the code out, the actual optimized code will just not have this in it. It's useless code. Right? Another common thing we could do is propagate values from one place to another and eliminate temporary storage and maybe eliminate operations in the middle. So again, if we take a look at this original piece of code, we can translate it to something that doesn't have the temporaries. It just does the math at the end, right, without the temporary storage, either on the stack or in fields. And then lastly, we can simplify math when we see it well ahead of time. And that math up there simplifies to x plus x. 2x or x plus x. The compiler could choose what instructions to use depending on what it thinks is faster. So all those are simple things the compiler could obviously do, right? Now let's look at some more compiler tricks that go a step above. First one has to do with propagating values in a way that affects the actual program flow, not just simplifies math or eliminates values. So take this little snippet, for example. We have a couple variables, and if the value is more than 10, we go do some sort of complicated computation somewhere else by calling it. But if the value is below 10, we set bias to 1. And then later we return whatever that is. Now, in this specific example, value is set to 5 up into initialization level. So the compiler is actually allowed to simplify that to this. Why? Because if value is 5, the if will only go one way. We actually could take it that way and say, oh, bias will be 1. We know it'll be 1. That's what we'll return. We don't need to do any other code except for return 1. That's a good example of, some interesting simplification, and there's obvious speed in doing this, right? Now, let's look at some other simple things that the compiler is allowed to do. Some of these might be surprising to people or might change what you think your program does. Let's take this simple program where we read a.x and 2 different lines of the code, right? There are 2 different things computed here that use a.x. Notice that a.x, a is up there, the point class is up there, and x is an integer field that is not volatile. The compiler is allowed to cache non-volatile values that it reads. It's allowed to read it only once and use it as many times as it wants within this. Now, the meaning of this is exactly the same if you ignore the fact that other people might be changing a.x. And you're allowed to ignore the fact that other people might be changing a.x because it's not volatile. So if somebody else went and changed a.x between the first 2 instructions, and you executed that code as written, you would get a different result than if you executed the code as it is down here. That's a simple read elimination or redundant read elimination. You can also eliminate reads in more surprising ways. Well, not surprising ways, but more impactful ways. See that loop? Running on a flag, counting how many times it runs until you set the flag externally to something else. The compiler is allowed to convert that to this. And this loop will never exit. Right? That's what volatile is for, right? You're not supposed to loop on non-volatile variables. Well, you can do it, but, you're taking a little bit of risk. The reality is that most compilers will specifically avoid or try to avoid doing this because this level of surprise annoys some people. But they are allowed to do it semantically. Okay? Now, just like we can eliminate reads, we can eliminate writes. So take this example where we change the same variable 3 times to 3 different values. Compiler is allowed to just change it only once and to pre-compute the value to change it into and simplify it. Yes, there were 3 writes, but hey, maybe I could have done them so fast nobody else could see them. So we're allowed to do it only once. That's a powerful optimization. Again, this is not a volatile variable. And you can also apply it in loops. So for example, we have a visible value here and another visible internal value there. That loop will set the value to whatever the counter on the loop is, right? Compiler is allowed to basically figure out what the last value in the loop will be and eliminate the entire loop. That's okay. Nothing wrong with that, right? And here you can see a lot of speed, right? I mean, that's a long loop. Okay, so we played with some simple things you could do within a method, right? Change order, eliminate code, propagate values, control flow, cache reads, eliminate writes, they're redundant. These are all good examples of simple things we could do in the code, right? The next step is to look at inlining. And inlining is really one of the most powerful things in optimization, not because of the simple fact that inlining eliminates calls, but because inlining exposes additional optimizations. Take this, for example, as a simple case for inlining. We have a class, we have a method in the class. The method is final, so we know that nobody will override it. There's only one get x in the entire world. And at some point later, we call that get x, right? Now, get x is simple. It's got only a single statement in it. The compiler is allowed to take that statement and later convert it to a direct field access on the thing without making a call. It's a very simple inlining of a very simple statement, right? So that's what inlining is. We take the call and we kind of make it code in the middle of where we are instead of making the call. Now here you're allowed to do it because you know exactly who you're going to be calling. It's a final method. Inlining is very powerful because you can use it to combine things. So for example, if we take this right there and take the compute bias method altogether, right? And actually, I think I made this accidentally recursive. But ignore that little faux pas. Imagine that the compute bias in there is a different compute bias. So you're calling the outside method here with a constant. Now, if I called it and I actually made the method call, the method itself doesn't know what value would be, so it can't simplify the inner code to do anything with it, right? It might need to call the internal computation, or it might not to. It need to call it. But if I inline compute bias at that site, I can propagate the value 5 through the code. Because at that site, it's a constant 5. Some other site might pass a different value, but at that call site, 5 is the value. And if 5 is the value, you can work through that code and figure out the result will be 1. Always. And the entire method collapses away. No call and no computation. That's an example of the power of this. And this happens recursively. Inlining within inlining within inlining will give you a wider scope for the other optimizations to find good things. Inlining a switch statement with a constant parameter eliminates the entire switch statement, for example. Okay, so far we were looking at normal compiler tricks. So everything I talked about so far happens in pretty much any optimizing compiler you can use today. It doesn't matter what the language is. It doesn't matter whether it's a static or dynamic compiler. Everything we talked about could be done analyzing the code, and that's it. It's provable things. But in JIT compilers, we have the opportunity to do more than that. We have the opportunity to speculate. And the opportunity to speculate really comes not from the fact that we see dynamic code, but from the fact that we can recover from wrong speculation. So if you can speculate, and then you find out that it's wrong, and you can actually change the code as a result, which only is doable if you have a compiler running in a runtime rather than pre-compiling everything, then you can speculate in some very interesting ways. Let's look at a couple of examples of that. First one is class hierarchy analysis. How many of you know what class hierarchy analysis is? Okay, a few. So good. I'm going to teach you something here. Class hierarchy analysis basically is a feature of most JVMs where you analyze the entire set of loaded classes and derive some things you can prove about the current set of loaded classes that is true as long as it doesn't change. When a new class is loaded, you have to reevaluate everything. You have to say, wait, did this break some assumption I made before? But until a new class is loaded, we have some things we can prove. Speculating that a new class won't be loaded, or at least it won't contradict this. So we could basically do global analysis, and we can find things about inheritance and method overrides, and we can actually make optimization decisions that depend on this and need to be taken away if the speculation is wrong. So we have to reevaluate if we are wrong. Now, an example of this is inlining without the keyword final. How many of you regularly make all your methods final? Stop doing that. It gives you 0 speed. Okay? If you're doing it because architecturally that's what you want to do, make sure nobody ever overrides this functionality, then good. Right? That's architecture. But if you're doing this because you think it makes your code faster, because I showed you that inlining, all JIT compilers and all JVMs for the last 15 years have been able to inline code without the keyword final just as fast. And this is how that works. Here's the same method we talked about before, not final. Imagine this is a class animal of some sort, right? And we have dogs and cats and birds, and they all have getColor, but none of them overrided getColor. They still just use the base class getColor. It's not final, but nobody has bothered to override it. Not in our world, not in our class hierarchy. So we could take that line that calls animal getColor and inline it and simplify it. And we can do it because the compiler basically proves that in the current universe there is a single implementer. Final or not doesn't matter. This one thing is what makes Java field access clean and simple and doesn't force you to put finals in front of them. So getters and setters are usually trivial functions that are field access, but allow you to make nice object-oriented calls rather than expose the insides of an object to an implementation. Right? And it allows you to do that while still allowing for the implementation to be extended. Right? So this example is simple and provable, and it'll remain this way until somebody loads another class, like, say, a chameleon. And a chameleon getColor doesn't just return a constant color like the rest. It actually looks at the tree branch it's sitting on and checks to see what color that is and returns a color based on that. So now, when we loaded a chameleon, the assumption that this is the only implementer is no longer correct. The JIT compiler or the JVM at load time will first throw away any code that depended on an assumption, any optimization, then load the class, and then we'll reevaluate. Now, throwing away is a deoptimization, right? It's driven by class loading in this example. So we can do a lot of other interesting things with what we call an uncommon trap. Hotspot usually uses this term, other JVMs might use others. An uncommon trap is basically the thing you put in the code that says, I assume this will never happen, and I didn't generate correct code for this, so go there and throw away my code and run something else, like the interpreted code or some other version of the compiled code that's not as optimized. Now, for example, we can speculatively assume the callee type, even though we can't prove what it would be. So take an example of the call I just made before. We have an animal.getColor call. And right now in this universe, there are multiple implementers, right? There's dogs and cats and birds that use the same implementer, but there's a chameleon that changed the implementation. So I can't prove that I'll call a specific one. But my code happens to be an animal.getColor that's sitting inside a dog kennel, and the dog kennel only gets dogs. So in actual experience, I will only see dog objects, and dog objects have this implementation of getColor. Now, if this remained true, it would be safe for me to call a specific method rather than do a vcall. It would even be safe to maybe inline it. We use the different terms. Polymorphic is the general object-oriented term for things that could have multiple implementers here, right? But we use terms like monomorphic, megamorphic, and you might even hear bimorphic to describe a polymorphic call that has only one actual target in practice or has multiple targets, that's a mega one, or exactly two would be a bimorphic. And we can then make the call to a monomorphic site if we just prove that the type is what we think it is. So rather than make a virtual call and figure out where to go, you could say, if this is a dog, call that, otherwise uncommon trap. Or otherwise fix this code. In this specific example I just gave you, it wouldn't be an uncommon trap, there's a in-place patch. But that would be the logic. Go and assume this will be the same, do the fast thing. If it's not, do something slow, right? So calling the direct target is one thing, but we can also inline that target. Speculatively, we could say, if this is a dog, then get the field color and just keep going. But if not, uncommon trap. So we can apply all the optimizations to inlining on the case we were right and just uncommon trap in the rest. We can do this not just for class hierarchy analysis and not just for types. A good example would be to look at speculatively deciding which way a branch will go. So take this example. Again, I'm repeating myself a little. We look at this code, and it could go either way. But we have run it 10,000 times before we decided to optimize this. And every single time in the 10,000 times, the value was less than 10. And because of that, it always just went through the second path and not through the first. The compiler can decide to do this. I would like to assume that I will never see a value bigger than 10. Because if that is true, I can apply some interesting optimizations. And those optimizations can be which way to branch or maybe what I can propagate as a value out of that. And those are very valuable. But they're only true if I never see a value bigger than 10. If I do see a value bigger than 10, well, I could have decided to generate all the other code that would deal with that, but in reality, that blows up very quickly because there's combinatorial effects. There's optimization, optimization, optimization. So basically we say, I don't think that will happen. Uncommon trap. If it does, throw away this optimization because it's not valid code. So that's where the uncommon trap will go. Another very powerful and very common optimization is here, null check elimination. So semantically, Java has to check every reference access you make to see whether or not the reference itself is null. So when you actually write x equals foo x there, what the actual machine has to execute is if x is null, then throw a null pointer exception. Otherwise, do what you said. And this is true for every single axis and every single field or every array field that you access. If the machine actually did that, it would take a huge burden on every operation, right? That would be slow. And yeah, you might be able to combine one null check for two fields, but it's not that big a win. What the JVM actually can do is to say, I don't think I'm going to run into a null, so I won't even check. I'll actually blindly go and do the access. What could go wrong? Well, what could go wrong is you got a null. And if you got a null, you're going to get a seg fault because you're going to be accessing a range of virtual memory that's not mapped. And if you get that seg fault, well, the JVM will intercept the seg fault, say, whoa, before I say crash, let's see where that came from. Oh, I got it on this field access that I assumed will not be null, so it must have been null. So take the stack, do some interesting surgery to it, move it so it looks like I was 2 instructions back, and you throw a null pointer exception. Very complicated, very slow to do if you take the null pointer exception, but they're not supposed to happen, right? And very fast because we do 0 checks, 0 anythings. It's actually the code as you said with no protection. This is a very powerful optimization. I've played with turning it on and off, and on many applications this is worth 10 to 15% speed on an application. There's a flag to turn it off if you want to play with it. Now this works very well and it's very fast if there are no null checks, if there are no nulls, or if they're very, very rare. Unfortunately, there are some places where it's common to encounter nulls, maybe half the time. And while this is much faster than checking, when you do take that segv, it's extremely slow. You take a virtual memory trap, you switch over to the kernel, it builds a segv, you go handle the segv, you run this much code that is not actually very well optimized, and then you finish. So if you run into a piece of code that does this a lot, what you want to do is throw away the optimization, put the null check in, because you'll actually run faster with it, because throwing the exception is much faster than going through all that segv handling. So it depends on whether this happens a lot or not. And applying the optimization is speculative on it not happening a lot. Now, luckily, just because of coding styles or correctness, most people don't actually throw a lot of null pointer exceptions in normal code in their behavior. But it is, again, as a kind of a tip to you guys, if you're writing code that basically works on the assumption that, it's okay to throw an exception as a control mechanism, don't do it if it's a common thing. Because the JVM in general will tend to assume that exceptions are exceptional. And they're rare. So it'll tend to optimize for them not happening. And then if you do them a lot, then it'll either throw away other optimizations or it might not throw them away and just go really slow. So just be aware. This is a common example. Okay, so deoptimization is that mechanism for taking the speculative assumption away, right? If we adapt, if we're able to adapt, we can go faster if we're right, because we can revert back if we're wrong. Now, micro-benchmarking, as a lot of you know, is a black art. Figuring out how fast code is alone, without any of this, takes a lot of careful, avoidance of over-optimization. You might write code and the compiler might figure out what you did and return the result of your code without running it, right? This happens a lot in micro-benchmarks. The art of warming up code is even harder than that. Because you might run the code and warm it up and it got to be the speed you wanted, and then it changed its mind, because the optimization can occur after you've warmed up for all kinds of reasons. And they often occur after you think you are stable. So it's not enough to let it run enough. You need to run through the right enough. And the right enough is something you don't necessarily know about. So there are lots and lots of causes. I gave you a few examples. But a common example of doing this would be a trading system. The market is about to open. I don't want to run interpreted through an open market. So let's warm the system up. How do we warm it up? Well, I've got some trades from yesterday. Let's run 20,000 of those through the system to let it warm up, because I happen to know that the compiler thresholds are 1,000 and 10,000. After 1,000, I'll do the C1 compile. After 10,000, I'll go do the highly optimizing C2 compile. So if I go through this 20,000 times, it's going to go optimize the common paths. And this is a correct statement, right? So we give it fake trades, right? But they're fake trades. And because they're fake trades, we don't really want them to go to the open market, right? So we do something that says it's fake, don't send it. What really happens? Well, we basically take that really, really nice code and optimize it for 20,000 occurrences of not sending to the market. And we have a smart compiler. It looks at goes and says, they never send anything to the market. I will optimize for not sending to the market. What happens the first time you have a real trade? Deoptimization. Right? That was a really, really nice warm-up you did. But it was so nice that it assumed you're going to keep doing that. And this is a good example of how the optimization at market open happens. You can warm as much as you want. If what really happens is not the situation you ran in warm-up, then the optimization of your critical code will happen. And this is a simple example. It can happen to parts. It can happen to a lot. Now let me give you an example of this in actual code. This is not the trading example, and this is an example of deoptimization that happened because of late initialization, of getting the code to run fast and wanting to optimize before all the initializations have occurred, which is actually very common. For example, you only ran through one protocol and you're hot, but the other protocol code hasn't even been loaded as a class. And then later you see that protocol code. Okay, so what we're going to do is look through a lazy optimization and initialization, which is normally how Java works. We have two classes here. I call them thing1 and thing2. This is from a Dr. Seuss story. And then we're going to have both, basically both of these classes have active calls to the same method, but the JIT compiler is going to kick in without ever calling one of them. So one of them will get hot, the other one wouldn't even be called yet, and the JIT compiler, it's sent 10,000 times around the loop. We don't know if the other one will ever get called, but we want fast code. So we try and compile code even though we don't have all the information to compile all of it, because one of the targets doesn't even exist. So as a result, the JIT compiler is going to generate code for the stuff it can and put an uncommon trap on the calls to the part that can't yet be resolved. This is a common thing to do because there are many cases in code where you have some conditional checks to do something that really doesn't ever happen. And if you waited until it happened before you optimized to go fast, you'd be running interpreted forever. So let's look at this in actual code. There's a link down here to the GitHub version of this. Hopefully this is readable. Is this readable all the way in the back? Okay, good. So we have a thing1, we have a thing2. Both of them basically increment a value. The value is initialized to two different things. And then we have this loop down here that until we reach a threshold calls thing2, but after we reach a threshold called thing1. So thing2 will be warm first for the first 20 million calls, and then we'll start calling thing1. Okay? Now, when we run this, when we hit this first call to thing1 is the first time that this class ever gets referenced or accessed or done anything. That's actually when the class will be loaded, and that's actually when it will be initialized. It wouldn't be initialized until then. The reason it wouldn't be initialized is because it wouldn't be valid to execute this statement until the time that you call thing1 for the first time. Now, okay, this statement is simple. It says it's equal to 0, right? You probably could have prepared that. But what if it said that's what day it is, right? Then semantically it's not valid to initialize it before you actually call it, because maybe you would only call it tomorrow. When we actually run this, and up here you have the flag to use, print compilation, to get this kind of output. When you actually run this, you get this output. And green and the red are my highlights on the text. So over here is actually in the print compilation, test run being actually optimized. That is that loop, right? And it got optimized calling into thing2 over and over again. We ran for a while, and then we output this part of the poem. And after that, we basically start using thing1, right? When we start using thing1, we get this. That's what deoptimization looks like in a compile log. Made not reentrant. Sorry, made not entrant. It's basically saying I had this code, and it's no good because I just hit a false assumption. I hit my uncommon trap. I can't run that anymore. So throw it away. It ran for a while, and later it optimized it again. So over here, you see where it optimized that same thing again. It optimized it here, and then it re-optimized it there. And then it's done. Nothing happened wrong, right? The results are right, everything ran. This happens to you all the time, right? You just don't turn the flag on. But it made one choice, it ran fast for a while, then it changed what it's right and did something else. Now if I take the same code and, if I take the same code and force initialization on the classes before the code starts running. This is an example of how to do that. There are many ways to force initialization, but over here I wrote a force init method, and basically in the static initialize for the whole thing, I force init these two classes. That means that both classes will be loaded and initialized before the loop even starts. And then we run the same code, we will get this behavior. By the way, in the program, if you give it any parameter over here, it will just force initialize. Okay? So now we ran, we compiled, and no deoptimization happened. Okay? Better. Now, it's better, because no deoptimization happened, no slowdown, right? Anybody notice something interesting with the numbers? Exactly. So see this? This one, without the optimization, took just over 2 seconds. The previous one took 1.3 seconds. What's going on here? Well, if we, oops, my slides are. If we look at this code, in the first case, it optimized for only this happening. And that was fast. And after it threw it away, it optimized for only this happening. And that was fast. So we ran fast, then we slowed down to the optimize, then we ran fast again on the other case. In the second case, both of them were ready, so we optimized for the possibility of either one happening, and therefore it ran slower. But it didn't deoptimize. You sometimes will face this as a choice between running fast or running without a blip. This is a common hard choice in optimization or deoptimization. This is kind of artificial. It's fairly rare that a program will do this and move from exactly always this to exactly always that, because most of the time when you have stuff, it'll happen a mix in the real world. But the example this would be good for is any situation where at the beginning of the program you do one thing, like load a lot of data into a cache, but later you never touch it and you only read from it. And a phase change in complete behavior of the application will have that, where you could actually be faster if you optimize separately for each phase. Okay, so that's our code in a good case, or in a non-deoptimizing case. So other examples of deoptimizations that can happen, well, we talked about the first call to a method that's uninitialized. I just showed you that. We can have a call to a not yet loaded class. That's a different thing. If the class is loaded, it may still not be initialized. Dynamic branch elimination to the unexpected path. The example optimization I showed you before could be taken back. And implicit null checks are good examples. There are about 12 others. I'm not going to get into the list here. Now, every one of these could be a reason to take things back. And every one of these may have different ways to work around taking them back. Because. Now, remember, this is what we have. We have a warm-up phase where we learn what is common. We optimize for what is common. And then we'll have that we were wrong parts. And then we'll go fast again. What we really want is to run fast all the time, right? Now, it's hard to deal with this, partly because it's complicated. You have to go read the logs to figure out that it even happens to you. Just because you had a blip doesn't mean one of these happened. But you could do all kinds of things about it, like find out, what the optimization events are, dig through this and say, okay, I understand what happened here. Let's do something to avoid it. Like initialize the classes that are ahead of time to avoid it, right? I showed you an example. Or make sure you warm up both sides of the code before, and make sure that you don't let the first 1,000 or 10,000 iterations do exactly the same thing when it changes later. You can prevent some of these manually. There are useful ways to do that. And it's beyond the scope of the next 6 minutes that we have here. But you can also look to use JVMs that have features to deal with it. We have a JVM that does. It's something we've been working on for a year and a half, or a couple of years. We've been shipping for almost a year. There are others that have done some parts of this as well. One of the powerful ways to deal with this is to basically log and replay optimizations from entire day runs before. So for example, you can log all your optimization information, the decisions you made, the stats that you made, and remember them. And if you've done this for an entire day, you've dealt with what actually happened during the day, including the wrong decisions you made. So the eventual thing you have at the end of the day is presumably the well-adapted code. You then read those logs into a JVM at startup or prior to actually running any code and sort of prime things so they're ready to go. Now, this is a tricky thing because you can't just go and take the code from yesterday and apply it. And you can't just say, I start up, I'll apply the optimizations right now. Because it's actually invalid to apply certain things before they're initialized. I gave you the example with a variable that changes every day, but it's static. So you have to wait until semantically you're allowed to apply the optimizations. So you have all these optimizations, and you have dependencies that need to happen before they can be applied. And once those dependencies are there, you can apply that optimization. We actually do that, basically track them across. Now, when you do this, you may find that some optimizations haven't yet happened. Why? Because the code that they're waiting for hasn't yet run. Maybe you didn't initialize thing 1 yet. Right? We can't go and apply the optimization until you do. It was applied yesterday, but it's not ready to be applied now. So one of the things that you can build is a workflow that allows the developers, the operations people, to know what has not yet been applied. So here's 5 things that were optimized yesterday but have not yet been used in this run because they're dependent on these 17 things that have not yet happened. Now, if you have that information, you can then work to resolve that information by making those things happen. Your goal operationally would be to reach an empty list where everything that was optimized yesterday has been applied to today's run before the market opens or before you start your new version of the app server. Remember, this is what we have. Let's start slow, blue, 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 and then deoptimized and reattend. And what we want is no slow operations or no slow startups that are real operations, right? It's okay to warm things up slow, but you don't want any real users or real trades to experience that. So no slow is our goal. If we look at it pictorially, that little dip is the optimization. So what you need to do is avoid the optimization. That will flatten that dip out. Now, separately, we have this warm-up thing, which people complain about as well, because sometimes it's hard to warm it up. Sometimes it's hard to know what 20,000 things to throw at stuff. If you actually load things in from a previous run, you can completely flatten that. So after the first initialization of anything, it's completely optimized, and before it ever runs, it'll be fast. So we have a product that does that. It's called Zing. And it does this, including the workflow part that lets you have the confidence that it actually applied. So a big part is not just to try and do it, but to tell you what's not been done so you can actually fix the world so it'll get to a 0 list. And if you want to think about it as a one-liner takeaway of our approach is, we look at this as just another form of hiccup. Garbage collection pauses are a hiccup. Deoptimization slowdowns are a hiccup. Lock debiasing JVM pauses are a hiccup. We address hiccups. So what we really focus on is making things run not just fast, but fast all the time. And this is a good example of an entire field to deal with there. So with that, I have 2 minutes left for questions. There's a microphone around? And so if you want to raise your hand, we'll get the mic to you.
Can you do some things if the application change, if the software change to keep optimization for the next version?
Can you do something at the application level rather than switch your JVM for that? I don't think so. Not today. It depends on the JVM that you use. And for example, if you use regular hotspot, either OpenJDK or Oracle, there isn't a feature right now to remember optimizations from the previous run. Once the optimizations have happened in your run, they're there. They're good. But you need to make them happen. And the feature to log them and read them again is, that's a feature of specific JVMs. Zing, I know that IBM in one version or another was working on it too. I think there's a request for Oracle to work on it as well, but I don't know of any specifics other than ours that work right now. So it says time up. Can we take one more question before we click? One more question? Over there?
As far as I understand, you use it for trading system. Do you have some numbers for typical desktop application, like IDs or this kind of thing, that your JVM brings?
So we have customers using it for trading systems and for things like matching engines. We also have customers experimenting with it for regular web applications, just in a flow where if you have a large cluster, you flip over just the first one, you produce a log, and then the other 99 members just read that log so they don't have to learn the same mistakes again. We don't have numbers for desktop applications like IDs. And honestly, we focus more on eliminating the dips and the slow behaviors than how long from the time you start the JVM until things are fast. Because in servers, usually that's not the problem. Usually you can turn the server on, let the storm of compilations go away, and then send traffic to it. A human in front of a desktop cares about different things. They care about elapsed time in seconds or parts of a second from when you clicked until the JVM is up and running fast. And that's a different problem, not the problem we focused on. Hopefully that answers that. Okay. Well, thank you very much. Enjoy the rest of the show.